Since we're going to be working with complex forcing functions, we should review complex numbers. Complex numbers have both a real and imaginary part, and that imaginary part is based on the imaginary operator. And we're going to use J instead of I. You've probably learned about I in mathematics. We use J so we don't confuse current with the symbol I. So our complex operator J is the square root of -1. So when we square J, we end up with -1. If we cube J, however, we end up with -1 times J, so we end up with -J. And then if we multiply that by J again, J to the 4th is equal to 1, and J to the 5th then is equal to +J. So not always obvious, but clear if you understand that J is equal to the square root of -1. So our complex number itself can be written in rectangular form or in polar form. We'll show it here in rectangular form initially, and we'll use for our variable k, that's a complex number, that is some a plus jb. Again, J is our imaginary operator, that's otherwise known as I, and we're using J in circuit analysis. And note that this variable K, it's not an italicized Time Roman font, it's a bold Time Roman font to show that it is in fact a complex number instead of just a real number. But we can take the real part of K, and that's A, and the imaginary part of this complex number K is B. So the imaginary part doesn't include the imaginary operator. We just say that's the imaginary part of the complex number K. In this case, we're using K. So if we were to graph that, we could put that onto our imaginary versus real coordinate system. So in this complex plane here, we have imaginary versus real. And if we're going to take the complex number m, which is 3 minus j2, well, that's 3 on the real axis, -2 on the imaginary axis, and here's our point m. Our n, 2 plus j, is +2 on the real axis, up 1 on the j axis, and here's our complex number n. Now 3, we're using r for our complex number 3. This is a complex number because a real number is a subset of the complex number. So our real number 3 just sits here on our horizontal axis, which is our real axis, and it sits here at position 3. And we could have just an imaginary number, just j4, and that's going to sit up here on the imaginary axis. So that's our complex number and our complex coordinate system. We can add complex numbers. If we were to add a plus jb to 3 plus jd, we add the real part and we add the imaginary part. So we end up with a plus c, that's our new real part, and b plus d, that's our new imaginary part. When we're adding, we can work with these just like we worked with vectors. So we can take our, if we let m be 3 plus j1, so here's our m vector. So our m vector, real 3, imaginary 1, and we draw in our vector here. Our n, which is 2 minus j2, so 2 in the real, minus j2. So here are our two vectors where the length of the vector, again, is representing the magnitude of this. We can convert that to angle. But if we're trying to add them, then what we do, we can create a trapezoid, right? So we take our m and we slide that down, and there's the m slid down here. Here's the n slid up, and we end up with this trapezoid, and our result is here in the middle. Our m plus n is 5 minus j1, right? So we can show that graphically, or we can add them simply by adding the real part. That's 5. 3 plus 2 is 5. -2 plus 1 is the -1. So there's the result of that. Multiplication, if we're trying to multiply, well, we can use our foiling, for example. We just basically the distributive property, right? So we want to multiply these. It's like multiplying binomials. So we have the real part, A times C. For the first, we have the imaginary part is going to be J B times C plus A JD. So we have our J times BC plus AD, but when we take our J times B, JB times our JD, that's J squared BD. Well, J squared is a -1, so this ends up being negative. So our real part becomes AC minus BD, and our imaginary part becomes BC plus AD. So once we do the FOIL, we end up with the 4 terms, but the 4 terms, 2 of them are going to be imaginary and 2 of them are going to be real. But one of the real ones is going to be real because it's multiplied by J squared, which is a -1. So we end up subtracting that. So that's how we can multiply our complex numbers. Dividing complex numbers, what we have to do here, if we want to divide these in this rectangular form, what we do, we have to make the denominator real, right? So to make that denominator real, we multiply the denominator by the complex conjugate. So if you note here, this is C plus JD, this is C minus JD. So the conjugate negates the imaginary part of the complex number. So then when we go and multiply it, in our numerator, we have AC minus AC, excuse me, AC minus, this should be, so here's the AC. This should be AD. Yeah, I have BD there, but this should be an A. Oh no, that's correct. So we have our AC, that's this term here, and then we have our JB times negative JD. So that's how we get the plus, right? So we got JB times negative JD. So this becomes plus B times D because we get the negative J squared. And then for our imaginary part, we just end up with our BC, right? There's our JBC, and then we end up with minus JAD again because the negative part. So that we pulled the J out over here, right? So there's our J. That's hard to see, so I'll erase it. But there's our J there. And then, but our denominator, we end up with our C squared plus JDC minus JDC. So the imaginary part cancels, and then we just end up with our JD times a negative JD, so we end up with plus D squared. So we end up with both of these have real denominators, so we can convert this to just, this is just, there's just one number, so that's your new, that's your new A plus JB, where A is equal to AC plus BD over C squared plus D squared, and your B is equal to BC minus AD over C squared plus D squared. So that's how we can divide complex numbers and get one complex number in regular form where we multiply the denominator and the numerator by the complex conjugate of the denominator. So that complex conjugate is the key here. So if our complex number A here is A plus JB, the conjugate, here's the symbol that we use for conjugate. The conjugate of that is A minus JB. So here we negate the imaginary part. If we add a number to its complex conjugate, we end up with a totally real part. The imaginary parts cancel. If we subtract an imaginary number from its complex conjugate, then we're going to get A minus A, so the real parts cancel, and we end up with whatever, JB minus a negative JB, so we end up with 2JB. So we end up with just an imaginary number. If we multiply a complex number by its complex conjugate, then we also end up with a real number, and that's what we did on the last example of division. All right, so that's your complex conjugate. Make sure you understand what that is from the perspective of a complex number in real form. If we look at our Euler's identity, then this was the Euler's identity we introduced in the last video. We could also write e to the negative j theta is equal to cosine theta minus sine j theta. So whereas this was positive, we ended up with a positive. When it's negative, this is negated. So if we want to get the reverse of that to determine what is the cosine of theta, well, if we add these two numbers together, we end up with the cosine of theta is equal to 1/2 e to j theta plus e to the negative j theta. Whereas the sine of j theta, if we subtract these two, we remove the real part, we just end up with 2 times the imaginary part, but it's negative, right? So we end up with negative j 1/2 e j theta minus e to the negative j theta. So with these two, we don't have to memorize the cosine and the sine, but we can solve for the cosine and the sine in terms of the the complex exponential representation. So the other form that we might want to use our complex number in is in polar form. So we can convert to polar form just like we do with vectors. So if we have our a plus jb, remember we put this on our complex coordinate system, where imaginary versus real axis. So if we have our a is going to be equal to c cosine theta, and our b is going to be equal to c sine theta. So here's our this is a and this is b, right? So here, and this is our a plus jb. The magnitude of that, the length, is our a squared plus b squared, and what we have over here, well, I guess if this is the number, we have our c cosine theta and our c sine theta. So that's converting back and forth using our Pythagorean theorem and using our geometric trig here. All right, so an exponential form of our number again, that theta, that's fine. That theta is going to be equal to the tan inverse of b over a as long as a is greater than 0. As long as we're in quadrant 1 or quadrant 4 of our complex coordinate system, then this is going to be true. However, if a is less than 0, if we're over here, the theta we want is the angle from the positive real axis, right? So that's the theta that we want. So if we just do our tangent function, remember, only returns between plus and minus 90 degrees. So that's why it only works over here in the first and fourth quadrant. So we need to correct for that to get the right angle if we're in the second or third quadrant. So be careful of that. If a is less than 0, we have to correct by plus or minus 180 degrees. So again, here, this is just showing that one more time here. And it's showing that we have to our e to the j tan inverse of b over a plus 180 degrees when a is negative and b is positive. All right, so our polar form of the complex number, we have rectangular form, we have our exponential form, c e to the j theta, and we have this polar form. So the TI calculators, TI-84 and TI-83, you have to put your number, your polar number, in this form here, where you'll actually use an I instead of a J. If you have a TI-89 or some of the other engineering calculators, specifically ones that are used for electrical engineering, you'll be able to put your number in this form, just c times the angle theta. Again, where theta in general is our tan inverse of b over a as long as a is greater than 0, and it's equal, the c there is the square root of a squared plus b squared. That's the magnitude or the length of the vector. That's the angle of the vector relative to the positive x-axis. So when we're multiplying numbers, it's much easier to do that in polar form. So if we're multiplying these two numbers, we just have to multiply the magnitudes and add the angles. So that's why the polar form is really important to us, because we end up multiplying numbers a lot. If we're dividing, we just have to divide the magnitudes and subtract the angle. So it's the numerator divided by the denominator for the magnitude, the numerator angle minus the denominator angle for the angle. So that's our review for complex numbers.